Today, I present to you our paper GSparsity, Unifying Network Pruning and Neural Architecture Search by Group Sparsity. This work is done in collaboration with Abasela, Yannis Kuiper, and Yang Yang. We consider the training problem with the L2-1 norm regularization, which is also called group sparsity, and which allows us to decompose the vector of trainable parameters of our network into different subvectors, as you can see here, for example. And group sparsity forces all the weights inside a group simultaneously to 0. As you can see, the L2-1 norm is a non-smooth convex function. And so whenever the optimization problem is convex and non-smooth, commonly used methods like stochastic subgradient descent methods converge only very slowly. Therefore, we use the proximal stochastic gradient descent algorithm, which is able to converge fast and provable to a stationary point. For example, we can use this for filter pruning. So here you see a convolution with 3 output channels. What we can do is we group all the parameters of each filter into their own respective group. So in this example, we obtain 3 different groups, and now say that after training, all the parameters of the second filter have been forced to 0. This allows us then to safely prune away the second filter. The same can be done for operation pruning. So here we group all the parameters of a certain operation into their own group. Note that for parameterless operations, we introduce a scaling parameter, and basically this allows us to prune away parameterless operations whenever the scaling parameter is forced to 0. Now, after training, all operations where their weights have been forced to 0 can be safely pruned away. Now, this allows us to extend this also to neural architecture search, where the main idea is grouping the same operation across different cells. So this allows us then to, for example, introduce normal and reduction cells just by basically grouping all the parameters of the same operation across those cells. And therefore, we are able to cast neural architecture search as a single level optimization problem. And also it's not necessary anymore to split the training data set into 2 parts because we don't have any architecture parameters. After searching, all operations where their weights have been forced to 0 can be safely removed. So we have no performance degradation after pruning. Experiments on filter pruning have been performed on a ResNet 50 on ImageNet, and there our GSparsity method reaches superior performance at different sparsity levels. For operation pruning, we use a DARTS v2 network, and we train it for various values of the regularization parameter. As you can see, the accuracy of the retrained network after 38.4% of its weights are pruned is almost identical to the unpruned baseline. Also, we have no discretization error even when the pruning threshold is only modestly small. For neural architecture search, we do experiments on CIFAR10 and CIFAR100. And as you can see, our method reaches the highest mean accuracy with low standard deviation on both tasks. We also obtain similar results on ImageNet and NASBench 201. So in summary, our group sparsity method is able to bridge the gap between network pruning and one-shot neural architecture search. It's very flexible. It allows us to do kernel, filter pruning, operation pruning, and NAS. Also, we are able to formulate NAS as a single-level optimization problem, and our method is able to reach superior and robust performance on filter pruning as well as neural architecture search. Also, we don't incur any performance degradation after discretizing the architecture because the method forces the weights of the groups exactly to 0. Our work can theoretically be extended by employing techniques from PC-DARTS or PDARTS, and we provide all the code and all our logs, they are all available on GitHub, so feel free to check them out. Thank you.